So that is basically the complete definition for the model form for log linear models. Again, we have some conditional probability of y given x under parameter values v. To calculate this, we compute the inner product between v and f. Remember, this is equal to sum k equals 1 to m of v sub k times f sub k of xy. And we compute the normalization term by summing over all possible labels y primed and taking e of e to the power v dot f of x and y primed. And this transformation basically takes us from these scores to a well-formed distribution over the possible values for y. So the next thing I want to talk about is how we actually estimate these parameters v from training examples. So we're in general going to assume that the set of features is fixed. So that's been defined coming into the problem, and the parameter estimation problem is going to be to estimate these parameters v from our training examples. Before I talk about parameter estimation, I want to talk about one other thing, which is where log linear models get their name from. Why are these things called log linear models? So the reason for that is the following. Why the name? So if you recall, we had py given x under v is equal to e to the v dot fxy over sum y primed e to the v dot f x y primed. So let's look at what happens if I take the log of this. Okay, so I take the log of p, I'm assuming log is the natural log. So the log of this is going to be log of e to the f v dot fxy minus the log of sum y primed e v dot f x y primed. This is just using the usual rules of taking a log of a ratio of two terms. And of course this is equal to v dot fxy because the log, assuming this again, this is natural log, and the exponent cancel each other essentially. And so what we end up with is this log probability being two terms. Here we have the inner product between v and f applied to x and y, where x and y are the elements we're interested in. And here we have log of this normalization constant. And so this is a linear term. That's why we call these things log linear models, because we end up with something which has a linear term as this first term. This normalization term is a function of x and so doesn't depend on y. That's the second term in this expression. Okay, so that's the reason for the name, and as we will see when we derive parameter estimates, it's going to be useful to bear in mind that when we take the log of p, we end up with these two terms. It'll be easy to manipulate things in this form.